So next up, we've got Nimrod, and he's in Mars with a background. But I am hopeful that this is another total geek fest, because anyone whose title has algorithmic machinery in that title gets us all kind of excited on the software side. So we are stoked to hopefully see some and hear some geeking out stuff. And with that, Nimrod, I'd like to hand it over to you. Let me make sure that you are, if you're not already, a presenter, a co-host, and you are.
Yes.
So my friend, take it away.
Hello. So can you hear me and see everything right?
Yes.
Okay, perfect. Yeah, so I'm Nimrod. Thank you for inviting me to this conference. It's a really nice, extreme idea to have a 24 hours conference. So I'm not sure how many hours you are already on, but hopefully you still have some power. So what I want to speak about is basically my approach on participatory budgeting, which is an algorithmic approach. So this talk is not very deep because I mean I wasn't sure what is the audience and what is the interest and the knowledge of people, but basically to give maybe the bottom line of the talk is that we should try to find good algorithms to help improve the quality of participatory budgeting processes. Okay, so this will be clear at the end, I hope. And if you want to ask things in between and in the middle, then please do. So I guess that all of us know what is participatory budgeting. Basically, you want people to decide on a mutual fund and how to split or use mutual funds for indivisible projects. This is at least the kind of participatory budgeting that I'm speaking about here. And this is the maybe abstract process of participatory budgeting. That is how I view it from an administrative way or algorithmic way. So first there is the phase where people need to assemble the set of projects. Usually it's done in cities, as far as I know, by letting every city resident to suggest a project, and then there is some committee by the city mayor that maybe filter some of the projects and also attach a price tag to each of the projects. So you have to decide on the set of projects that are available and on the total budget that you want to spend. And this is the first phase that I'm not going to speak about at all. So I assume that this happens. And then what happens next is that basically, if you want to conduct a PB process, a participatory budgeting process, then you have to decide on two things. First, you have to decide how you elicit the preferences of the voters. So basically, how do you ask people for their preferences regarding the project? And after you decide this, then you can collect the votes because you decided on the type of ballot or the way of eliciting the preference of the voter. So you have now the preferences, and then you have to decide how to aggregate the preferences. So these two things are very crucial. This is at least my point of view. And the way this is done usually is that you elicit preferences by approval. So basically, people can see the list of projects and they select they select a subset of the project that they approve of or like or want to see funded. So this is basically a binary decision on each project separately. And then what the city has is a set of many approval ballots, of many ballots of approval type. And then the usual aggregation method is what I call greedy approval. And it looks like this. So people can see this list of projects and they can select maybe upper bound of several projects or any number of projects that they select. And then what is greedy approval? What is this aggregation method is maybe the most natural thing. And this is what is done, as far as I know, almost all over the world. This is the only aggregation method used. So basically the city count the number of approvals that each project get, and then you can order the projects by the number of approvals in a decreasing order. Sorry, so for this instance, there was a project to plant 100 new trees, and this got slightly above 1,400 votes for approval. So it means that there were slightly above 1,400 ballots of this type where people selected this project. And then basically what you do, you go over this list until the budget is exhausted. So in this example, you fund this project, and then there is no more funds left. So this is the algorithm. This is the run of the algorithm for this instance that selects these 6 projects. Okay, so there is two things to decide. One is the elicitation method, and in this example, this was approval. And the second is the aggregation method. And in this example, this was BD approval. And now the question that I started to think about maybe 2 or 3 years ago is which elicitation method is the best and which aggregation method is the best. So in social choice, which is my field of study, there are many different elicitation methods and many different aggregation methods or aggregation algorithms. And each of them has different advantages and disadvantages. And it's not completely clear which one is the best for each setting. So usually the universe is more complex than that. And then when I first heard about participatory budgeting, I thought that this is a really nice idea. And I was very surprised to see that basically this type of process is the only type of process that people are using. So people only use approval elicitation or approval ballots and greedy approval as the aggregation method. And this seems to me very strange and also possibly bad. So this is why I started to think about maybe there are other things that are suitable and fitting for participatory budgeting. So the first thing to ask is, what is the elicitation method? So what are the most standard elicitation method that people are using in other settings? So there is approval ballots, as I said before. So you see there is the set of projects and people can select some of them. Maybe the standard model of social choice or the ballot type or elicitation method that is most studied is ordinal ballots. So people basically rank maybe all of the projects or some of them. So this is an example where some person preferred this project the most, then this project second, and this project third, and she didn't rank other projects. And there is a different, yet another elicitation method or ballot type, which is a cumulative ballot. So the way to think about it is that I give you one Bitcoin or one virtual coin, and you can split it among the projects as you like, basically specifying the intensity of your preference. So this voter put half of the virtual coin in this project, slightly less than third on this project, and so on. And then there are other elicitation methods, but what I think that we should first think about is why approval is the most popular ballot type by far, and whether this is really the best choice to take when we want to do PB processes. And actually my answer as of now is that I think that this ballot type is better, but of course, this is, well, there is not a mathematical proof of this kind of things, but the situation is more complex. But if I would if I would make some PB process, maybe I will use this elicitation method and not the standard approval method. So it's nice that you could recognize the shekel picture.
I used to work for, I used to be head of engineering and product management for Aladdin. Worked for Yankee, I worked for Yankee Marglit and Uzi Dvor and Avi Barir and a few other people. So shalom. It's been, I was done for portfolio management, PB in Elat.
Oh, okay. So do you want to say a few words about it? What was the?
Nope. Just it was fun to see a shekel.
Okay, good. So did you live in Israel or went to visit?
I didn't live, but this was a while ago. Just I traveled enough to Israel to wish I could eat the food more frequently because it's such good food.
Yeah, this I agree. Okay, good. Okay, so I'm going back to elicitation method, and please, I mean, if you have questions or you want to discuss things in the middle, then please do. Also about foreign currency. So there are many different elicitation methods, and I think that what is the most important trade-off or issue to think about when you want to select the elicitation method is this trade-off between expressivity and simplicity. You can find some other names for this, but this is the name that I like. Basically, the way I see it, if you want to do a high quality PB method, then your most pink dream would be to have a small robot that you can inject into people's brains, and you will know exactly the whole preferences about everything. And then you can collect these very invasive kind of preference elicitation, and you can possibly come up with the best outcome. So this is, of course, not very good, also for privacy reasons. But this is, I think, one of the most important things. So what you want on one hand is to find the elicitation method which will give you the most information, and if you view it from the perspective of the voters, this would mean elicitation method that will allow voters to be the most expressive. But what you are afraid of is that the ballot type and the process will be too complex for voters to participate in. So if you will ask voters for too many questions about the preferences, then they will get tired, and maybe you will get not very good answers. So this is why there is this inherent trade-off between expressivity and simplicity in choosing the elicitation method. But what I think makes things maybe better for more complex elicitation method is that I think that you can overcome most of the difficulties by designing a good user experience. So for example, so if you choose this cumulative ballots, then this is of course more complicated than asking for approval ballots. But if you want to design let's say an online system for this kind of process, then you can have approval ballot as let's say the simple case, and then you will have a button of advanced options. And then people who want to be more advanced and to express their preferences even more, then they can click this button, and then they can put in the system their cumulative preferences. So in a way, I think that on one hand, we should aim for building systems that allow people to be very expressive, and we should somehow overcome the inherent difficulty in the loss of simplicity for voters by designing nice user experience for simple-minded voters who don't want to make this kind of complex decisions, or don't want to use this kind of complex elicitation methods. So I will come to this also closer to the end, but I think that this is an important thing that maybe gives more room for more complicated elicitation methods. Okay, so let's say that we settled on one elicitation method, and now the second thing that we should decide is the aggregation method. So what is an aggregation method? Basically, you will have the set of all of the ballots, which are filled already by the voters, and you have the total budget limit that you want to spend. And now you need to build a machine that you feed to it all of the ballots and the budget limit, and it will it will output a set of winning projects, basically. And this machine should be somehow good, but it's not very clear what is a good machine, because there are many machines that will output different set of winning projects for different instances. And what is more important is that for a specific instance, basically a specific set of projects of ballots and a specific budget limit, then different machines or different aggregation methods would output different winning bundles or set of winning projects. So we should somehow have a nice way to decide how to pick the aggregation algorithm. And I mean, as I said before, so what is the most standard algorithm used? It is greedy approval, but it's not completely clear that this is indeed the best. So what is the best is also not very clear, but I will try to convince at least that there are other options that I think are more fitting for other settings. So if I read correctly, also Harris gave a talk maybe 4 or 5 hours ago about one kind of different elicitation method that I will also discuss a little bit, but there are many others. And now basically the main question is, how can you compare different algorithms? So you can view the sea of endless possibilities for aggregation algorithms or aggregation methods. And now you will end up with just many algorithms, many different ways of aggregating voter preferences for PB. But you also have to find a nice way to compare them, because you want to decide which algorithm you want to use. And there are several ways that we are using in our research to try to compare these algorithms. And you can maybe group them by these 4 things. So first you can, this is very abstract, and I will make this thing more concrete, hopefully, as we advance. So the first thing is that you can view this problem as optimization. Basically, you can ask yourself, what is the objective that you want the algorithm to maximize or to minimize? So basically, there are many possibilities for taking voter preferences and outputting a solution. A solution is just a set of projects that respect the budget limit. And different solutions will have different values for you. And if you can define in a good way what you want the value of the solution to have, which kind of thing you want to optimize for the solution, then you can use a mathematical tool to develop algorithms that will find really the solution that optimize for this specific objective. So just to give you one example. So for example, if you are developing a search engine and you want to optimize the ordering of the pages that you show the users by something. So maybe you want to optimize for the relevance or for the time that people are using the service and so on. And in a similar way, you can ask yourself, what is the thing that I want to optimize for participatory budgeting aggregation methods? And if you can define it in a good and exact way, then you can use mathematical tools to find it, to develop algorithms that will find it for any instance that you'd feed it. So this is what I call optimization. There is a different, somehow related, but slightly different way to try to design aggregation methods and also to compare them, is by basically writing a list of desiderata. So writing a list of things that you want the algorithms to have. So you can write this kind of list. You say, okay, what is my dream algorithm for aggregating voter preferences for participatory budgeting? It should be proportional, maybe, which means that it should somehow respect different minority groups or different groups in the population. And you can also define other kinds of axioms. For example, it should use all of the available funds. This is one possible property that maybe you want the algorithm to adhere to. So then if you write your preferred list of properties that you want the algorithms to adhere to, then maybe then maybe you can find an algorithm that will satisfy these properties. Maybe yes and maybe not. But then also maybe you can compare different algorithms based on the properties that they satisfy or the properties that they don't satisfy. So for example, there are many ways to define what is proportionality formally, but let's say if you take one specific way that we used in a paper with Harris, and then you look at the greedy approval method that is used currently for PB processors, then it's very easy to see that this algorithm does not satisfy this axiom or this property of proportionality. And then if you want to design the PB process, and for you the property of proportionality is very important, then the immediate consequence is that greedy approval is not the method for you to use, and so on. So you can use this list of desired properties to help you design the algorithms and also help you to choose the algorithm that you want to use for specific settings. I wrote here incompatible with the picture of arrow, just to hint that many times if you write your desired list of properties or axioms, then there is not a single algorithm that will satisfy them. I mean, so you can actually prove that there is no algorithm to satisfy some sets of axioms. So this just means that sometimes you have to be less ambitious in the properties that you want the algorithms to satisfy. But still, this is a very useful method, I think, to design and to compare algorithms. Third way to design and to maybe to compare algorithms is to do simulations and experiments, and this we are doing quite a lot. So we can do simulations with artificial data and also with real data, and for this real data ingredient we developed this website. It's Fabulib, so there are
join the meeting.
Okay, so there is basically, this is a database of instances of participatory budgeting that we collected. And then this is useful because if you have on one hand many instances of participatory budgeting, and on the other hand you have few or several algorithms for participatory budgeting, then you can run them. So you can run each algorithm on each of the data sets and look at the results and see what are the difference, and maybe analyze it post factum to see maybe which algorithm seems to be fitting to certain kinds of inputs. So this was the third pillar. And the fourth pillar is complexity. So if you follow these two pillars, if you either write your list of axioms or you define your optimization goal, then maybe you could design a good algorithm, but it could still be the case that this algorithm is not useful, in the sense that if you run it, it will take it 2 years to compute the answer. So this is maybe not useful in a way. So this is still a thing to watch out for. Basically, how easy it is to use the algorithm that you come up with, and this is also related somehow to the issue of explainability, because in many cases you want the algorithm to be such that it's not very hard to explain it to common people. I mean, if I use some advanced mathematical tools, then sometimes it's very hard to explain to people. And if you use machine learning, then it's even hard to explain it to anybody, because nobody knows what is done under the hood. But many algorithms, I think that they are fairly easy to explain to common people. So you can try to use them because people could understand them. Okay, is there any questions so far or comments?
Well, I only have one comment.
Sure.
Worrying about computational complexity, that seems like it would be unlikely to be a function of the number of items, because you would get bounded rationality among the actor if you gave them too many choices. And so it would seem to me that the only aspect of computational complexity that could rear its head would be in the number of voters. And so if you could get the entire population of a large city, let's say you go to India and you're in a reasonably sized city and you get 7 million votes. Okay, it would seem that the computational complexity would be more attributed to the participants and not the number of items, because the number of items are going to be relatively small.
I see. So what you're saying is that so let me rephrase what you say, and then you can correct me if I got it wrong. So what you're saying is that in most real-world instances, the number of items is not very big.
Yeah, I'm come on, you're Israeli, so we can debate, and I know how much you love it. And if we didn't debate, you'd feel awkward. So I'm just putting out a little debate. Like if you actually look at, if we're going to talk about computational complexity, there has to be some notion of cardinality that would motivate the concern. And I'm saying in my experience, the cardinality of the ballot is usually very low, because you get into human complexity on choice theory, on just if I've got more than say 15 to 18, 20 at the most items on a ballot, it can be overwhelming for a human actor. So I don't think computational complexity would be associated with the items, unless I'm not understanding certain algorithms that might be used.
No. I mean, I think that I agree generally, but still, I mean, even if you have, let's say, 100 items, or maybe this is also too much, but I think that in some instances, this is the number. So I mean, so I could agree that the number of items is maybe not in the thousands, but I think that it could be in the tens and maybe in the lower hundreds.
Yeah. And
then this could become problematic if your algorithm running time depends exponentially on 100. This is still this is already quite high, or at least could be high.
Fair enough. I'll let you keep going. In my experience, even in working in the corporate world, when we've seen large numbers of projects in the project portfolio, we've usually used tournament structures where we limit the choice set given to the participants, and then we would have different populations look at different subsets of the items and then aggregate them up like a swim meet, where you have swimmers compete and certain projects advance into the next round. We can take that offline, but I find this fascinating because if you get too many items, an individual can't make a choice because it just gets cognitively overwhelming.
Yes, yeah, this is really interesting. No, but so in your example, you simply assign subsets randomly to people?
Yes. You take the list, you randomize it, you then.
So this kind of random process, I guess that it works in a corporate world, but in a civic, political high-stake world, maybe it works less, no?
I think it's different. I think that would be an interesting area of consideration. My experience in the civic side, so in the private sector, it works pretty well. In the public sector, I've just advised the people I've worked with don't have more than 22 items, period. Like, just sorry, you just can't have that many because an individual can't process. It's too, we're moving from the mathematics of computer science into the mathematics of, or not the mathematics, but the techniques of choice modeling and market research, right? You at a certain point, you're just going to get overwhelmed. Harris wants to jump in. So Harris, jump in.
Yeah, I think I'd like to mention, I think we might want to distinguish between elicitation complexity, where I think Lucas has been mentioning more about how many items and somebody is expressing preference over, and computation complexity. So I think I really want to highlight Nimrod's angle here, that even if, let's say, everybody is expressing preferences over 10 items, at the end of the day, the number of outcomes to overall outcomes is going to be 2 to the power 10 possible subsets of projects can be selected. So the computer algorithm has to decide among these 2 to the power 10 different overall outcomes, and that's quite a large number, especially
Yeah,
if you care
I see
about.
what you're saying now. Yep, get it.
Yeah.
Okay, good.
Cool.
I'm glad we talked for a sec.
Okay. So let me continue with somehow a very, let's say, brief overview of different rocks that I try to summarize here really fast, just to basically give a more concrete feeling of my approach, at least to tackle this problem. So first, actually, we did this work with Piotr from Poland, and this point of view was this point of view, this optimization point of view. We said, okay, how can we find good algorithms? Maybe we can think about let's say happiness or the satisfaction or the utility or whatever, but let's speak about happiness of a voter that is facing some outcome. So, for example, let's say that there is a voter, and in this paper, at least we consider only approval balance. I mean, you can do the same kind of analysis, or you can try to do the same kind of analysis for different elicitation methods, but this is concentrating on approval. So consider a voter that votes for projects P1, P2, and P4. And let's say that you have an algorithm. I mean, I don't know how it works, but the algorithms outputs a set of projects P1, P2, P5. So now think about this voter that is voting for this. I mean, this is the ballot of the voter, and this is the outcome. And how happy is this voter? And if you can come up with a complete answer to this question, then you can then basically it gives rise to an immediate optimization objective. Basically, you can say, okay, so what I want to do, I want to design an algorithm that will make the most people the most happy, basically. And how you can define it more formally, you say, okay, so consider an outcome of the algorithm and consider all of the voters and just sum up the happiness value of all of the voters. And now what you want to design, you want to design an algorithm that will maximize the total happiness of the voters across the electorate. So the sum of the happiness of the voters across the ballot box. So now what you should answer is how happy is this voter? So you want to come up with a function that will tell you, that will output a single number for this voter when she faces this outcome. What is, I think, the most natural answer, but there are others. So in this paper, we consider several answers. But what is a very natural answer is to say, okay, this voter, she approves of 3 projects, and out of these 3 projects, 2 of them were really funded. I mean, were really selected by the city, and 1 of them, I mean, is not, right? So P4 is not funded, but P1 and P2 are funded. So the happiness of this voter is 2. This is one possibility. There is a different possibility. You can say, okay, let's say that this project cost $1, and this project cost $1 million. Or let's say different. P1 and P2 cost $1 each, and P4 cost $1 million each. So if this is the outcome, then maybe still the satisfaction or the happiness of this voter is 2, but if the outcome would be only P4, then the satisfaction or the happiness maybe would be 1 million, because maybe for a voter it's even better to have a smaller number of projects funded from the set of projects that she approves, but projects that are more important or cost more. So maybe there is a relation between the importance and the happiness that the voter would get from a project that she likes being funded. Maybe this relates to the cost or not. But if we take the simple, and there are other ways to define the happiness of a voter from an outcome, which gives you different optimization goals for participatory budgeting algorithms. And then you can ask yourself for each one of them whether you can find efficiently the outcome that will maximize this objective of maximizing the total happiness of the voters. So let's go back to this maybe most natural happiness function, which means that the happiness of the voter is simply the number of projects that the voter approves of and that are being funded. So for this voter, this would be 2. And then you can also say, okay, can we develop an algorithm that will maximize this value, this happiness, this sum of happiness values of the voters? When we define it this way, and actually you can do this, and this is very related to this standard greedy algorithm or greedy approval algorithm that are being used. Because if you think again about this greedy approval that I showed before, and this is the most popular aggregation algorithm, in a way, this algorithm tries to maximize this value. Because, I mean, if you think about it intuitively, why this algorithm orders the project by decreasing order of the approvals? Because you want to catch as many approvals as you can. But quite simple and important observation is that this greedy algorithm does not optimize indeed this sum of happiness values as I defined it before, but it only gives somehow usually a good approximation, but only approximation value for this. And actually we can use a different algorithm that would really optimize this value. So my semi-formal claim is that actually this greedy approval algorithm is just an approximation algorithm for a different algorithm that you can design, and it's not very hard to implement also, that really optimizes for this value. So in a way, this greedy approval algorithm is only a substitute for the real algorithm. And I think that at least you should use this algorithm that really optimizes for this value and not this greedy algorithm. So I hope that this is understandable. Okay. So in this paper we develop similar kind of algorithms for different optimization goals, but I think that this is the most suitable or natural, at least if you don't care for proportionality. So Harris, you were speaking about this paper before when I was still sleeping.
I think I mentioned proportional concerns in general. I did not go into approval base too much. I focused more on this this update version with ordinal preferences. So,
okay, cool.
But it wasn't in too much detail.
Okay. I mean, I also didn't plan to go into much detail, as I wanted to know. So what is the most important observation for this? I think that in many cases for participatory budgeting, as Harris, I guess, spoke also, you want the outcome to be proportional. So for example, if you, I mean, the most standard example that I always give is that if you have a city with 2 districts, one district has slightly more population, so let's say 60%, and the other got only 40%. And let's say that all of the voters from district A vote for project in district A, and all of the voters from the other district vote for project in the other district. Then if you use either the greedy approval or the optimal approval algorithm that I discussed before, then what you will have that only project from district A will be funded, because each of them will get 60% of the vote. And all of the projects from district B will not be funded because they only get 40% of the vote. So this is maybe not very desirable, and this is why we thought about this, how to find participatory budgeting algorithm that somehow solve this problem. I mean, this is an extreme case of this problem, and the intuition is that what is the property that the algorithm should adhere to? So this follows. Let me go back to this general idea. So this last paper that I discussed follow this optimization idea, but now we follow this axioms idea, and we try to define what is proportionality and find an algorithm or several algorithms that can satisfy this property of proportionality. And we define it to be something that follows this kind of intuition. So each group of voters that are large enough and cohesive enough in the sense that they vote for roughly the same project, or at least they have a non-negligible set of projects that all of them approve of, then they should not be ignored, in the sense that you should find at least some of the projects that this large and cohesive group approves of. And so, for example, this district B in this example is very cohesive because we said that all of them vote for all of the projects in district B, and they are fairly big because it's 40% of the votes. So the intuition says that in this instance, we should have roughly 40% of the public funds to be used in project in district B. So this was the general idea behind this work. And it turns out that sometimes we run to issues that there is not, and I mean, there are no solutions at all that can satisfy these desires. Some other times we run into problems of complexity, but maybe for real-world instances, this is not a real problem, as we discussed before. So maybe we can use also other algorithms that search in the space of solutions, not very efficiently, but still in reasonable time for real-world instances. And for some other cases, we could find really efficient algorithms that are guaranteed to work fast for basically any instance. Okay, so let me go on to a different work we did, and here we change not only the elicitation method, not only the aggregation method, but also the elicitation method. And the main starting point of this work was that in a way it feels that for participatory budgeting, cumulative ballots are very good. So this is only a feel, but in a way, I mean, because at the end, what participatory budgeting is doing is taking a budget and splits the budget to projects. Then it seems suiting that also we can use this idea of splitting money as the elicitation method. So cumulative ballots, I mean that the ballot is different in the sense that each person got this 1 shekel that she can split as she wishes among the projects, as I showed before. And then we say, okay, so let's say that this is the ballot type, and now we have to find an algorithm that gets as input many ballots of this type and output the solution. So this would be a very different algorithm than the algorithm that we saw before that were working for approval ballots, or the algorithm that Harris showed before for ordinal ballots. And for this, we came up with this idea of the algorithm. I mean, we have a concrete algorithm which is slightly more technical than what I present here, just because there are certain fine computation that you have to do. But I think that, as I said before, I mean, it's very important, I think, that for the algorithm to be explainable easily to common people. And so what I try to do is to convey the general idea of the algorithm, and the details are deferred to the paper, let's say, or to later. So this is the general idea. It follows generally the idea of STV or alternative vote, which is the same. So you can view this 1 shekel that so you can view the total budget limit that you have as a stash of coins. I mean, L is the total budget limit that the city wants to spend on participatory budgeting. And now view the process as you are not giving just 1 coin or 1 virtual coin to each voter, but you simply split the total budget limit to all of the voters. So for example, if you have 100 voters in the city, and the budget limit is, you have $1,000 that you want to spend, then you can simply give each voter $10. So this is what I draw here. So now each voter has $10. And now what does voters do? So here you can see in this example, there are 4 projects: school, hospital, police, and fire department. And each voter, basically, we said that he splits these coins to different projects. So for example, consider this voter above that I gave her, or the L over 2 coins that I gave her in this picture. She gives to school, and point A she gives to hospital. This basically means that she likes the city to fund the school and to fund an hospital, but her intensity of preference is more higher for hospital. So she gives more support to hospital. So how can you view this ballot of the voter? The way I like to think about it is that each project has a glass beside it, like I draw here. And the height of the glass is just the cost of the project. So school cost C of P1 is just the number of dollars that school cost. So we have a glass of height which is equal to the cost of the school, and so on for each of the projects. And now you can think about it, because I said that I split the money among the voters, so each voter gets L over N coins. And now 0.2 of this L over N coins, this voter puts in the glass for the school, and point A she puts in the glass for the hospital, and so on, all of the voters. And this is how I view the ballots of the voters. And now basically what you have, you will have glasses for each of the projects, and some of them will be more full and some of them will be less full. Some of them may be even overfull, I mean, with water dripping from the sides. And now what we want to do, we want to do an algorithm that will take these glasses and will decide which projects to fund, right? This is the aggregation algorithm. And the algorithm works in steps or iterations. So in each step, we are looking at the glasses. If we see a glass that is full, that we want, then we want to select a project whose glass is full and fund it. The question is which project, if there are several projects whose glass is full. So this is one option. And if we are in the option in which none of the glasses is full, then what we want to do one of two things, either to fund the project whose glass is the most full, in the sense that it's closest to be full, or we want to take a project who has not a chance. I mean, it looks like it doesn't have a chance to be funded, so his glass is very empty, and we simply eliminate it and take the water and put it to other projects. So let's say that we find the project whose glass is full. So we basically drink all of the water according to the cost of this project, and we say, okay, so this police department is already funded, and we used the funds to fund this police, but now maybe there is also excess water or excess coins. Then we move it, we basically ship it to other projects, still based on the preference of the voter. So you can view it as you basically drink the water that you need, or you take the coins that you need, and all of the excess you bring it back to the voters in proportion to the number of coins that each voter gave to this glass initially. And then you look at the ballot of the voter and you split it again to the other project that this voter supports. So basically it means that you take some water and you put it into other glasses. And this would mean maybe that now for the second stage, so in the beginning, this hospital was not full, but now maybe after we took the excess coins and put it in the hospital, and maybe now this hospital is full, and then we can fund it, and so on. So this is what we do. I hope that it's understandable, and also you can see that I think you can explain it maybe better, but you can explain it to common people. And what we found is that it gives a solution which are proportional, and it also gives high voter happiness in the sense that we discussed before. So just to give one example, so we took data from a participatory budgeting process in Warsaw, in Poland, in 2019, I think. And we were taking the voter ballots, and we change each ballot to be a cumulative ballot just by splitting the coin evenly among the project that the voter approves of. And then we can see that we still get high happiness, and and the outcome is proportional. So this is a algorithm that I think works very, very well for cumulative balance. It somehow also gives a nice balance between happiness and proportionality, which are also inherent trade-off between them. Okay, so I think that we are almost running out of time. So let me just end with rather quickly with some things that I think we could aim for to even push forward the applicability of participatory budgeting. So there are certain issues that that we are currently not dealing with when we're doing participatory budgeting, at least as far as I'm concerned, or at least as far as I know. So one of them is interactions or relations between projects. So far, what we said, okay, there is the set of projects, and people can express their preferences, but they express the preferences separately and independently for each project. But I think that in many cases there are interactions between projects in the sense that, for example, this person, maybe he wants to fund a school, but only if there will be a bus stop next to it. So if in the PB process there will be one project for school and one project for bus stop, but I mean 2 different projects, then this person faces a not very convenient choice of what he wants to do. So, and let's say that this example is of approval ballot. So this person could say, okay, so I will approve the school and I will approve the bus stop. So I will put a check mark in school and check mark in bus stop. But then still it could be the case that if we use one of the algorithms that we discussed before, then the output would be that we will fund the school. I mean, the school will be selected, but the bus stop will not be selected. And then this voter will be rather disappointed, right? Because, I mean, he somehow used his 2 approvals to the school and to the bus stop, but he thought implicitly that this would mean that, that either none of them will be selected or both will be selected, because this is what he wanted originally. And this is an issue that I think is important, at least to certain people. And what we try to do here, we try to offer a possible solution to this. One solution is the following. So you can take the set of projects or the items, and you can split them to groups. And let's say you will put the school and the bus stop in the same group. And then you can try to find an algorithm that will basically take into account the interactions between the projects based on this partition of the projects into groups. And how can you do this? So you can define, for example, for a certain group that there is a diminishing returns, or I mean, which is like a negative correlation or negative synergy, and also positive synergy. So what is negative correlation or diminishing returns? It means that a voter that approves, let's say, the school will have, let's say, a happiness of 1 if the school will be funded. But if both of the projects will be funded, then maybe the happiness is even greater than 2, because there is some interaction between the projects. So if you can define this kind of diminishing returns or increasing returns between groups of projects, then it turns out that you can find good solutions that will optimize this kind of solutions when you take into account the interactions between the projects. This is one idea to somehow push the applicability or the expressivity of voters in PB. And also for this, I think that if you think about the good UX, good user experience that will allow it, then this will be more useful. This is one thing, and the second thing is related to geographic districts, but also to diversity constraints. So one of the criticism for PB, as far as I know, is that if you give people the choice between which projects to fund, that maybe all of the people will choose to fund let's say, projects that only relate to recreational activities, but not projects which relate to infrastructure, for example. And this could be problematic for the city. And then we thought about, okay, maybe we can plug this into the process as well. So what we did here, we say, okay, let's say that we have the set of items, but the items have also types. So some items, I mean, this item could be for recreational, another item could be for education, this one is for culture, and so on. And maybe we can define lower bounds or upper bounds on the budget that you will spend on each project type. So for example, you can say, okay, we have projects in the city center, we have projects in one of the suburbs or several suburbs, and we want to restrict the algorithm to find solution in which you do not spend more than, let's say, 70% of the funds on the city center. Or you can say things like, do not spend more than 60% on projects which relate to transportation, because you want to also reserve enough funds to other kinds of projects. So in this work, what we did, we basically tried to find algorithms that will find solutions that still optimize the happiness of the voters, the satisfaction of the voters, but still adhere to this kind of constraints. So this means this turns the problem into a much more complicated problem from a computational point of view, but still this can be done usually. So for example, if there are not, I mean, if the number of constraints is not very big, then still there is a relatively simple algorithm that will find an optimal solution even when you respect these kind of constraints. So this is the kind of thing that we try to do here. Okay, this I said also. Okay, so actually we also did another thing when we asked real people for basically what we wanted to do is to ask people for what is the algorithm that they think is the best. But because it's hard to ask people about algorithms, but it's easier to ask people about solutions, then we designed the human study in which we showed people inputs for participatory budgeting, basically sets of ballots, and different solutions. Each solution is using or derived from a different aggregation method. And then basically we ask them to cross the solution that we think is the best, that they think is the fairest or the best. And we got some interesting answers. Okay, so the last thing I want to show is this Pabulib, this website with the database of PB instances that we developed. And let me maybe end here, because the time is already over.
Do you have any? Hi, do you have any further closing words? Because this is really great. This is, I mean, I'm geeking out and loving everything that you and Harris are sharing. I've been chatting with Harris while you've been talking, and it's very exciting stuff. I've been doing this work since 2006 inside corporations, and framing it in a more academic way and getting the benefit of formalisms is really exciting. And looking at some of the work. I have a potentially challenging question. The current company, right? My last company built portfolio management software for large entities using participatory budgeting techniques, or at least a variation of it that we use. And we helped organizations around the world manage more than $3 billion in portfolio spending through participation techniques, online, widely distributed teams, and different places around the world. So now what we're doing at FirstRoot is we're looking at building solutions for schools to give direct money into the hands of kids so they can invest it in their school through participatory budgeting techniques. So a question that I would have is, if you were to pick an algorithm based on its explainability, we know that greedy algorithms are understood by kids, but what other things might you advocate as a means to help a child understand what we're thinking about, or what this is, not in a mechanism of what an adult could deal with complexity, but for a child of, say, primary school, and maybe a child who can deal with more complexity in elementary school. Like, what algorithms might we advocate to get kids civically engaged and to promote PB?
Okay, I mean, this is a really great question. So if you only care about simplicity, then I guess that greedy approval is maybe the most simple algorithm you can use, right? This you can explain really in one sentence. You say, okay, so I ordered a project by the number of ticks, and I found them. This is basically what you do. So what I have in mind, I mean, let me first ask a question. Right? So Jews always answer the questions by first asking. So I will ask a question and then I will answer.
That's okay.
But it is one of the reasons, or one of the goals, is to doing PB in school is for education. I mean, to somehow help them think about the money spending, and then, I mean, help them advance by education means, or?
Yeah, absolutely. We have two educational objectives, because we think participatory budgeting is really compelling in two educational domains. The first is the core elements of financial literacy, things like total cost of ownership, operating expenses versus capital expenses, line item budgets. So, and the notion that the students are in control of actual money, which helps them think about how to spend it, right? I mean, as a father of 4 kids, I know for sure they spend money differently when it's my money versus their money.
This is true.
Right.
As
and so, so at one level, right, the goal is to create, especially for low income or minority students who don't have access to money, and they're good at cash flow, but they're not good at letting money sit. One element of our PB program is they have exposure to financial literacy. The second element of education is in positive civic experiences. We created a proposal, and we get to ask the students, using some aspects of design thinking, who would desire this proposal? Is this population serving everyone in the school? Is it serving a subset of students in the school? Is this a subset of students who has a special need? Would it benefit you, or does it benefit the future? Like, what kind of benefit? So we did a project that we completed just a few weeks ago with an elementary school of 5th graders, which are kids who are about 11 to 12 years old in the US. And there were 3 classrooms, about 58 kids, determining how to spend about $1,500. And they bought a tree, or they funded a tree for the school that they planted. They funded getting new soccer nets and equipments for the soccer field. And they voted for fidget toys for the kids, some toys. That's okay. I mean, part of this is they have to be able to choose and experience the pros and cons. And so for those kids, that's part of the reason I'm asking is there may be, in the design of the company, we may trade off a more fair algorithm for an algorithm that is more understandable and explainable to the students themselves.
Yeah, I see. Yeah, so I mean, there is a question whether proportionality would be really a major thing for you, right? Because I mean, I could imagine a classroom which is with, I don't know, with two groups, racial or gender or I don't know what. And then, I mean, it could be the case that some of the kids would feel left out, right? Because I mean, at the end, the process will fund only project of the other group. So whether this is a real problem or not, I don't know, of course. But if this is a problem, then my first thought would be, I mean, you can use this also to educate about algorithms, right? Because
Absolutely.
I mean, because this is relatively easy to show kids. Okay, if this is your votes, if we use this simple algorithm that we explained, then you will get this. But see that almost half of the kids will be left out. So then maybe you want proportionality. I mean, this is
absolutely. Yeah. I mean, this is actually, for me, this is part of the educational experience. Just like in our process, the ideas are generated, the proposals are generated by the students. They might find that the worst thing they spent their money on were the fidget toys. Okay, how are you going to learn? And so I'm not opposed to having a poor outcome that could occur because we have a teacher who's in there helping them explain, like, okay, look at what happened. Is that what we want in a civil society? What do we want as part of the experience? And that, you know, it's kind of hard to set up. And I'm not a rubber bumper American parent, meaning I don't walk around trying to prevent every mistake that can happen, because first, I don't think that's very good for the children. And second, I think it's an impossible task. So that's why I'm bringing this up, because our goal is in fact an educational outcome. And that doesn't mean that we're going to try and optimize like we might in a city. But Harris, jump in, please.
Yeah, I just want to mention one approach which simultaneously captures fairness and also explainability, although it's not very simple. So let's say you have $1,000 you want to use, and there are 100 kids. Now, one way would be that you ask the children that how would you want to use them. But another way, which actually is very well aligned with autonomy and discussion and deliberation, is to at least give all the kids a fake $10 and let them just decide by talking to each other whatever they want to do and see where it goes. And that is quite likely to lead to a fair outcome, because everybody's going to be using their $10 towards something they like. And they might pool in their resources and find something of much better value. I think it might lead to a lot of nice activities.
Yeah, and Harris, that's exactly the algorithm I implemented in my last company for portfolio management. The only difference would be to maximize collaborative behavior. We would take those 40 participants, put them in a group of 5, and let's say the portfolio budget, just for easy math, was 100 million. We would give each of the participants $20 million. And in fact, we would sometimes print out Monopoly money if we were in person. And if we were distributed, we would use the software platform that we created. But it was that exact structure of taking the budget and distributing it equally among the actors. The only, I think, difference was that we would group the actors so that we would maximize the interaction within a group. And then we would treat the result of a group as a single result and then aggregate the results of the groups.
That sounds like an excellent activity.
Yeah, I'm just checking with you, and because the research could show other aspects, but this is, again, very exciting because, you know, in the long-term dream that we have is that the platform that we're building itself would have very clear controls over selecting one or more algorithms, and that the students themselves could, say, 1 year in 9th grade participate with one algorithm, and the next year in 10th grade participate with a second algorithm, and in 11th grade participate with even a third algorithm. So they could start to really experience, like, what does this mean when we're engaging in these manners and having these choices?
So let me suggest yet another algorithm, the last one.
Yes.
So you can view the greedy approval algorithms as follows. Basically, you look at the ballots, and each ballot has a set of projects that they approve, and the weight of each ballot is 1. And now in each iteration, you want to select a project whose total weight is maximized. Right? This is the same. This is a somehow weird way of looking at greedy approval. And then basically, I mean, you can do this with pencil and paper, right? So you take the ballots and then, okay, this is the project of the highest weight, and now I cross it off from the ballots and I put it on the side because I found it. And now you can change it a little bit in the following way. So in the beginning, the weight of each, I mean, you simply draw the weight of each ballot to be 1. And now in the first iteration, this is the weight. But let's say that you pick some project because it has the highest weight and you cross it and you put it on the side. But then you also change the weight of the ballots that approve this project. So for example, if there is a ballot that you crossed because you approved this project, then now you change the weight of the ballot to be not 1, but to be half. Basically, you give a fine to this ballot. And then you can do this. So, I mean, if there is another project that you found from this ballot, then you change it to 1/3, 1/4, 1/5, and so on.
Mm-hmm.
And this is, I think, relatively simple to understand algorithm that will achieve some kind of proportionality. So, I mean, it's fairly easy to find examples where this solves this proportionality extreme cases. Because basically, if you think about these 2 districts, in the first iteration, all of the projects, all of the ballots from the first district will be rated to be half. So then in the second iteration, you will basically go back and forth in funding projects from district A, district B, district A, district B, and so on. So,
yeah, and that's the kind of algorithm that I think would be approachable by kids in a secondary school. I think in a primary school, I think that algorithm would be a little challenging. But I think as the kids aged and they became more familiar with the process of engagement, this is the kind of algorithm that could be made accessible, and we can certainly program it, and then we have another option for them. Oh, this is brilliant. Okay, any other members of the team that we have? Any questions or choices? All right. Well, I believe that I'm up as a speaker next. My question is, my team knows how we're building our software. Harris, would you and Nimrod like to hear this talk, or do you have other things that you'd like to do? I'd like to make sure that you have the option to be engaged or not engaged as you would deem appropriate.
So I'm actually already late for my second meeting, so I will have to run. But it was really nice to be here. Thank you for inviting, and if you want to discuss more in the future, I will be happy.
Is it the next one?
Yeah, for me, it's the next one. If you'd like to stay for a little bit, I don't know if you saw my.
I'd love to. I just have to pick up my daughter from daycare at some point, which is between 4 and 5, and right now it's 4:10. So it's. I will start watching it.
How about I go in 20 minutes? Yeah. I'll just go through this very quickly, and you can kind of see how we're using agile techniques to build this.
Yeah,
this is good for me also.
All right. Oh, great. Well, thank you, Nimrod, again. If I manage to get back to Tel Aviv, which I would love to, I'm going to add you to my list of friends to have a cocktail with.
Perfect.
Okay.